Okay, just like cylindrical coordinate system, we have another coordinate system called spherical coordinate system. And these things are quite important. Well, for example, when we get to integral, the fourth part of the book, the integrals over surfaces, things like Stokes theorem, Green's theorem, they're like double integrals and things like that. You should yourself, you should decide what kind of coordinates is better to use. So maybe the question is written in rectangular coordinates, but you should understand, you should decide that the problem is not really, we can't solve it in rectangular coordinates. We should write everything in spherical or in cylindrical coordinates, and then we can compute the integral. So that's the motivation. Sometimes we should go to other coordinate systems to solve some of these problems. Okay, so in spherical coordinates, a point, say P, in the space is represented by a triple, which we show them with rho, theta, and say phi. And what are these numbers? Well, rho is the distance between P and the origin. Make sure that you are not going to confuse rho with R. R was something else. So if we look at the shadow of P on XY plane, R was the distance of that point with the origin. But rho is the distance of the point itself to the origin, not the distance of its shadow. Okay, so here we have rho, one of the numbers. We have two angles, theta and phi. What are these angles? Well, I should say rho is distance, so it's greater or equal than 0. What is theta and what is phi? Okay, so again, like the previous case, we can look at the shadow of P on the ground. We showed with P prime. We can look at the segment, the vector which connects P prime to the origin. The distance, that distance now is R, which we don't care about that anymore. Actually, here we only care about the rho. Now we can look at the angle this blue vector makes with the positive direction of X. We call that theta. That would be the angle theta. What is phi? There is another angle. What is this phi? Well, if you look at the point P, the vector which shows the point P, that vector itself makes an angle with Z, with positive direction of Z. That angle is phi. Okay. So, and phi is, there are some restrictions. Phi would be always between actually 0 and pi. We would understand that better in examples. So how can we go from rectangular coordinates to spherical coordinates, and how can we go back from spherical coordinates to rectangular coordinates? Okay, so from spherical to rectangular, it's a simple geometry problem. Actually, you can do it if you're interested. It's trigonometry. X would be rho sine of phi cosine of theta. Y would be rho sine of phi sine of theta. Z would be rho cosine of phi. Okay, that's the way to go from spherical to rectangular. How can we go from rectangular to spherical? Well, rho squared is going to be x squared plus y squared plus z squared. Theta would be arc tangent of y over x. Phi would be arc cosine of z over square root of x squared plus y squared plus z squared. So these are the ways one can go from spherical coordinates to rectangular coordinates, or from rectangular coordinates to spherical coordinates. To be honest, I don't memorize these things. I derive these relations each time using a little bit of geometry and trigonometry. But I think probably for you, especially for the exam, it would make more sense if you memorize them. Well, it's your decision. It's a good practice. You can see if you can derive these equations by yourself or not. Now, I should just say one thing. So let's go back for a second, especially for the people who do physics. Here, the first number row shows the distance between the point and the origin. The number theta shows this angle. The second number shows this angle. The third number shows this angle. Now that's in math literature. In the physics literature, they completely changed the order of theta and phi. So, you know, in math, when they write theta, they really mean this angle. The notation theta is for that angle. And if they write phi, they really mean this angle. The notation phi is for that angle. In physics, it's completely different. So they use phi for this one and theta for this one. So just for you to know, if you're reading a physics book, in order not to get confused, that's different convention. They're just the other way around. Okay, so we have these formulas to go from spherical coordinates to rectangular coordinates, and from going to rectangular coordinates to spherical coordinates. Okay, so let's use these coordinates. Let's use them. So, for example, if you have a point P, x, y, z equals to, say, 2, 3, 4, what would be the coordinates? Find the coordinates in spherical coordinate system. Okay, that might be a simple question in the exam. So 2, 3, 4, we want to find it in spherical coordinates side or the right side. Well, we have the point in rectangular coordinate system. We want to go to spherical. So use right. So I would use the description we have on the right side, and we should use the description on the right hand side. Okay, we need to find, well, what is the description of P in spherical coordinates? Is going to be rho, theta, and phi, and I need to find rho, theta, phi. What is a rho? Well, rho squared is 2 squared plus 3 squared plus 4 squared. It's 4 plus 9 plus 16, right? Okay, what is that? Well, it's 29. So rho is square root of 29. We take the positive one. It's going to be plus or minus, but we only consider the plus. We wouldn't consider the minus because it's distance, and distance is a positive number. What is theta? Theta is arc tangent of y over x. What is y? Okay, y is 3. What is x? It's 2. So theta is arc tangent or tangent inverse of 3 over 2. Can you look online? What is, can you look using calculator? What is arc tangent of 3 over 2? Let's see. Well, it's 0.9 radian. Oh, 56 degrees. Okay, thank you, which is almost the same as 56 degrees.
Wait, I
Okay,
have a question.
Yeah.
Sorry. I might have written this. Oh, never mind. I wrote it down incorrectly. Never mind.
No, say it. It's okay.
No, I thought it was. I was gonna ask because I already did it, and I was doing when I was doing theta, I did arctan y divided y over z. I didn't realize it was y over x.
Oh yeah, it's y over. It's always y arctangent of y over x. Yeah. Yeah. Good. So what about phi? Phi is no. I mean, in the exam, if you would have it, it would be. I told you there are just some specific angles which I expect you to know, like 0, pi over 6, pi over 3, pi over 4, pi over 2, pi. I don't expect you to know what is the tangent of 56 degrees, right? I wouldn't expect you to know that in the exam. The things in the exam would be these like important angles. Okay, phi would be arc cosine of z over, well, what is z? Z is 4 over square root of 29. What is arc cosine of that? Can you compute it? I think it's pretty small angle, right? Oh, 42. Okay, I was wrong. How wrong I was. So it's around 42 degrees. So the coordinates of this point would be almost something like square root of 29, 56 degrees, and 42 degrees. That would be the coordinates in spherical coordinate system. Now we can go the other way. So we can go from spherical coordinate system to polar coordinate system. So let me write down the equations for the other way again. So x would be rho sine of phi, cosine theta. Y would be rho sine of phi, sine of theta. And z would be rho cosine of phi. Now, if a point P is given, and if it's if rho theta and phi are equal to, say, 1, pi over 6, and pi over 4, we want to find the coordinates of P in rectangular coordinate system. Okay, so we need to find x, y, and z. Well, what is x? X is rho, which here is 1, sine of phi, which here is pi over 4, cosine of theta, which here is pi over 6. Sine of pi over 4 is the square root of 2 over 2. Cosine of pi over 6 is the square root of 3 over 2, so it's the square root of 6 over 4. So that's x. What is y? Y is a rho, which is 1, sine of phi, which here is sine of pi over 4, times cosine, times sine of pi over 6. Well, sine of pi over 4 is the square root of 2 over 2. Sine of pi over 6 is 1 over 2. So it's going to be square root of 2 over 4. And finally, z is equal to rho, which is 1, cosine of phi. But cosine of phi is cosine of pi over 4, which is the square root of 2 over 2. So that would be the coordinates of this point in rectangular coordinate system. We can do that with equations too. If we do that with equations, we would get an equation. So let's just look at one equation, which would be pretty satisfying. For example, consider the equation of a sphere, x squared plus y squared plus z squared equals 1. This is in rectangular coordinate system. what would be the equation of this sphere in spherical coordinate system? Well, what was definition of rho squared? Rho squared was x squared plus y squared plus z squared, but this thing is 1. So rho squared is 1, which means rho is 1 because it's a positive number. So equation of a sphere in a spherical coordinate system is just rho equals 1. The sphere with radius 1, centered at the origin. The equation of that sphere is just rho equals 1. See, it's much, much easier and more satisfying than this quadric equation. Here we have a quadric equation, right? They're squared and there are 3 variables here. Just one variable equals 1. That's the equation of sphere in spherical coordinate system. So because rho squared is equal to x squared plus y squared plus z squared, and because x squared plus y squared plus z squared equals 1, it means rho squared is 1. So rho would be plus or minus 1, but because rho is distance, it's positive, so its rho is just 1. That would be the equation of sphere with radius 1. Okay. Any question?
I have a question.
Yeah?
Sorry, would you ask us to go from cylindrical to spherical?
That's a very good question. Actually, you just spoiled one of things I had in mind. So if I ask you to go, that was pretty good. If I ask you, for example, to go from spherical to cylindrical, one good idea is to go from spherical to rectangular.
And then go to spherical?
Go from rectangular to spherical.
Okay.
Yeah.
So there's no like direct formula?
There is direct formula, but why would do you want to memorize another new formula too? I mean, we already have a lot of formulas, right?
Okay.
Yeah, we can, yeah, sure. I mean, it's not even hard to derive the formulas between them, but I mean, we don't need to. Let's not confuse ourselves. If we know how to go from spherical to rectangular and how to go from rectangular to cylindrical, we can do that. Okay, so actually they are pretty close to each other because spherical is rho, theta, and phi, and spherical is r, theta, and z. So already they have theta in common. That would be the same thing between them. But you can find a direct way, but you don't need to. So we can just use rectangular coordinate system. So there's a question, what would be the equation of ellipsoid in spherical coordinate system? Okay, so ellipsoid, well, in general, ellipsoid would be, well, let's write down an example rather than the general case. Well, an example would be x squared over, say, 4 plus y squared over 9 plus z squared equals 1, right? This is in rectangular coordinate system. How can we go? Is it possible to write it down in spherical coordinate system? Can we do that or not? That's the question. Well, what do you think? Think about that for a few seconds. Can we write down, is there any way we can write down this equation in spherical coordinate system? Think about that for like 2 minutes. Yeah, think about it. Okay, let me write it down because I want to get to one more subject too. So x is r cosine of theta sine of phi. Y is r sine of theta sine of phi, and z is r cosine phi. So x squared would be r. So I would just plug in these equations into our main equation. So x squared would be r squared cosine theta squared sine phi squared over, say, 4, for example, plus r squared sine theta squared sine phi squared over 9, say, plus r squared cosine. It's cosine of phi. Cosine phi squared equals 1. Well, simply, that's our equation, right? Because it's something only in terms of r, theta, and phi. And remember, oh, sorry, I changed my notation, huh? Yes, you're right. This is rho. Yeah, I betrayed my own notation. I insisted that distance in spherical coordinates, the distance from the origin is rho. Yeah, so that would be the equation in terms of rho, theta, and phi. There is nothing complicated about that. We just used our equations that we just plug into this equation we have, and we would get the equation in spherical coordinate system. Okay, so let's go to one more thing I like to talk about, and that's not something new, but we talked about vector valued functions. So the subject of second chapter was vector valued functions. So this kind of helps us to compute, say, velocity and acceleration. So when we have a curve, say in plane, we have a curve like this. I said at each time t, we know where, if we have a parameterization would tell us where is the curve at different times. T equals 0, t equals 1, t equals to 2, and etc. So we can, using this, we can find two things. We can find, well, we have the position already, but we can find the velocity and we can find the acceleration. And the point is that we think about velocity and acceleration, both of them, as vectors. Not as numbers. Velocity for us is a vector which shows the speed, but also shows us the direction where the particle is moving. So that's quite important. When the particle is here, we say the velocity is the tangent line to this curve. Do you see this tangent line? This thing shows the direction at exactly that point, right? For example, the velocity at t equals to 0 then would be a tangent line. The length of this tangent vector would show you how fast this thing is going. And we would take that all just by taking the derivative. So velocity comes from taking derivative of the function. Acceleration comes from second derivative, derivative of derivative. Let's look at one example. Let's see how we can solve the questions about that. Let's say we have a particle, r of t, which goes around the unit circle in plane, right? Unit circle at the origin. The parameterization for this was cosine t sine t. Okay? If I ask you what is the velocity of this particle at time t, you should compute the derivative of this function. I would show derivative at a prime. So cosine t would be minus, derivative of cosine is minus sine, derivative of sine is cosine. And if I ask you to show it on the graph, what would be the velocity vector? It always would be tangent to the curve. So if I ask you what is the velocity at this point, you should say it would be tangent to this curve. If I ask you about the acceleration, you should take second derivative. So you should compute the derivative of derivative. You take derivative another times. Well, we take derivative of cosine once, we got minus sine. We take derivative of this thing another times, we get minus cosine. We take derivative of sine, we get cosine. We take derivative of cosine, we get minus sine. Now, what is the acceleration vector at each point? Well, if I, for example, ask you what is the acceleration vector at that point? Acceleration is always towards the origin. Its acceleration at this point would be this vector. It's the vector which points towards the origin of the circle. What is acceleration at the red point? It would be this point, this one. The vector which starts at that given point and points to the origin. What is the acceleration at the blue point? It would be this one. Okay? Does it make sense? Now, for example, we can have a slightly more realistic example. Suppose we have the sun here. Suppose this is, we are thinking about XY plane. Well, it's not very realistic actually, but it doesn't matter. Suppose you have XY plane. And suppose we have the sun here at the origin. Actually, it doesn't have those things by itself. So suppose we have the sun here. Okay. Suppose there is a comet or an object coming around. And because of sun's gravity, it would diverge a little bit from its path and then would go that way. Okay, we had an object. And this is the trajectory of that object. Okay. Okay, suppose this trajectory, which is a curve, is given by this function, by this parametrization, t squared minus 4 and t. It means x as a function of t is the first component, t squared minus 4. Y as a function of t is the second component. Right? This is given. So now the question is, find the velocity vector of this object. And what would be the velocity like at these points if you just want to sketch it at the red points? So the velocity is just derivative of this function. So it would be derivative of t squared minus 4, which is 2t. Yes, that's correct. And derivative of t, which is 1. And if I ask you to show the velocity vector at these two red points, you should look at the tangent vectors in direction of curve. If I ask you, velocity vector is usually shown by v of t. Rather than r prime, you can use v of t. The acceleration is the second derivative. Sometimes we use a of t. Okay, we should take one more derivative. Derivative of 2t would be 2. Derivative of 1 would be 0. It's interesting. Derivative is constant. Do you see? It doesn't depend on time anymore. Does not depend on t anymore. Right? 2 and 0. So the acceleration is always like this. 2 and 0 is this vector, right? Goes towards right by 2. So if I ask you what is the acceleration vector at those 2 points, you should say it's 2 and 0. This is this vector. This is 2 and 0. So at all these points, the acceleration is 2 and 0, which shows it's not actually a realistic model. But anyway. So now we can have the same thing in three-dimensional space. So suppose we have an object which moves, we have an object which moves in three-dimensional space along the curve. This is the parameterization. So what is the curve? What is the parameterization? It's going to be something three-dimensional. So let's say t cubed, and 3t. Find velocity and acceleration. So velocity would be derivative of r, which is going to be derivative of t is 1, derivative of t cubed is 3t squared, derivative of 3t is 3. That would be velocity. What is the acceleration? It would be the second derivative of r. The derivative of 1 would be 0, derivative of 3t squared would be 6t, derivative of 3 is 0. That would be the acceleration. Okay. Now, there is a way to go the other way. There is a way to go the other way. So what do I mean by that? Sometimes we have, rather than, yes, exactly. So here we had the curve. The curve gives us the position. And with r, and we took derivative, we got the velocity, r prime. We took derivative, we got the acceleration, r prime. Sometimes we have the acceleration. If we take integral, we get to derivative, we get to velocity. And if we take the integral again, we get to the position. So let's see one example of this phenomenon. Suppose we have an object which, there is one more thing we need to know for going back. I should add that. In order to go towards right, there is no additional information we need. But in order to go back, we need something called initial data, which I will tell you what it is now. Just look at this example. Suppose we have an object in three-dimensional space, which starts at the point, our object starts from rest at the point p equals 1, 2, 0. Okay? Suppose the acceleration of this object is equal to 0, 1, 2. Okay? It's, say, measured in feet per second per square, something like that. And then I want to find, the question is find the location of the object at t equals to 2. That's the question. Okay? How can we do that? So that's the theorem, the fundamental theorem of calculus. That's probably the most important thing in both math and physics. That if you have a location, you can take derivative, you get velocity. You can take derivative again, you get acceleration. If you take integral from acceleration, you would get velocity. If you take integral from velocity, you would get location. So here acceleration is given. I want to find velocity. Velocity is integral of the acceleration. So it would be integral of 0, integral of 1, integral of 2. What is integral of 0? Does anyone know? A constant, some constant. Let's show it with C1. What is integral of 1 t plus another constant? What is integral of 2t plus another constant? Okay, I want to know what is C1. I need to know what is C2, and I need to know what is C3. That's why we need the initial data. What is velocity at the time 0? Well, it would be C1, 0 plus C2, 2 times 0 plus C3, right? But look at the question. The question says the object starts from rest. It means at the beginning, it wasn't moving. So in the beginning, the velocity was 0, right? That would imply these constants are all 0. Okay, so we don't need them. I can erase these constants. They're just 0. 0t and 2t. Now, I want to find the position of this thing. I should take integral another time. So again, I would have integral of 0. I would have integral of t. I would have integral of 2t. What is integral of 0? Again, another constant, right? Let's call it C4. What is integral of t? T squared over 2 plus another constant. What is integral of 2t? T squared plus another constant. Now I want to find these constants. So I should look at the position of x at the time t equals 0. That would be, well, if t is 0, the initial location would be C4, 0 plus C5, 0 plus C6. But it already told me the initial position, the initial location. It said it's 1, 2, 0. Therefore, C4 is 1, C5 is 2, and C6 is 0. If I plug in those things here, C4 is 1. Then I have t squared over 2 plus C5, which is 2, and t squared plus C6, which is 0. This is the location of the particle at time t. Now, what is the question looking for? Find the location at the time t equals 2 seconds. So I want to know where the particle is when t is equal to 2. Well, I would just plug in t by 2. I would get 1 t squared over 2, which is going to be 4 over 2, plus 2, which is 4, and t squared. So at the time t equals to 2, the object is at 1, 4, 4. Is it clear? Is it clear what I'm doing here? Is there anyone who is confused? Just ask me. If you're confused, I would explain in more detail. Okay, there. Let's see. Is there a question? Yeah. So let's explain it. Maybe it's better for me to explain it one more time completely. So here we know if they give us the location, if I take derivative, I would get velocity. And if I take derivative of that, I would get acceleration. Also, the interesting fact is that if they give me acceleration, if I take integral, I would get velocity. And if I have velocity, if I take integral, I would get the location. Okay. Now, I know I have an object which starts at rest. The question is here. Sorry. It's a little bit lost in translation. So I have an object which starts at rest at the point p equals to 1, 2, 0. And the acceleration vector is 0, 1, 2. I want to find the location of the object at the time t equals to 2. Okay. So I have the acceleration, and I want to find the velocity. The velocity is going to be the integral of the acceleration. So it would be the integral of 0, 1, 2. The integral of 0 is going to be just a constant, C1. The integral of, so I can erase these things again and write it again. So the integral of 0 would be 0 plus a constant. The integral of 1 would be t plus a constant. The integral of 2 would be 2t plus a constant. I want to find these constants. So I should look, whenever I want to find the constants, I should look at the time t equals to 0. If v at the time t equal to 0 is equal to 0 plus c1, 0 plus c2, 0 plus c3, which is just c1, c2, and c3. So the initial velocity is c1, c2, and c3. On the other hand, the question says the object starts at rest. It means the initial velocity is 0, 0, 0, which means c1 is 0, c2 is 0, c3 is 0. So the velocity would be 0 plus 0, which is just 0, t plus 0, and 2t plus 0. Now I want the location. I should take another integral of the velocity. So integral of 0 would be another constant, c4. Integral of t is t squared over 2 plus another constant, c5. Integral of 2t would be t squared plus another constant, c6. Now I want to find these constants, c4, c5, c6. Again, I should look at the initial situation, the time t equals to 0. Okay, when t is equal to 0, x would be equal to c4, 0 plus c5, 0 plus c6, which is simply c4, c5, c6. The question tells us the initial point is 1, 2, 0. Therefore, c4 has to be 1, c5 has to be 2, c6 has to be 0. Therefore, x is actually 1, t squared over 2 plus 2, and t squared. That would be the location at the time t. The final question is find the location of the particle at t equals to 2 seconds. So we should we should plug in t by 2. So the first coordinate is 1. The second coordinate is t squared over 2 plus 2. Well, if 2 is equal to 2, it would be 2 squared would be 4. 4 over 2 is 2. 2 plus 2 is 4. And the last component is just t squared. It would be 2 squared, which is 4. So we would get 1, 4, 4. Okay, that was the end of section 12. That was the end of 12.3. On Thursday, we will learn about 12.4 and 12.5. Next week, we are going to have midterm. All of you, remember, if you do not attend the midterm, you are going to lose some points. Don't forget, attend the class. Oh, there is a, oh yeah. Well, there is a question. I saw that question. The answer is, actually, I don't have, that's not up to me. That's actually the department who is responsible for the format of the midterm. But I think there are ways to have a good exam. So, well, we can talk about that more later. So we are going to, on next week, we are going to, so we are going, on Thursday, I'm going to finish this chapter. And next week, we are going to have exam, and we are going to start functions of several variables. So it would be, in total, there are 4 chapters for us. We finished chapter 1. We will finish chapter 2 this week. Next week, we will start chapter 3, which, so chapter 1 was linear algebra. Chapter 2 was vector valued functions. Chapter 3 will be functions of several variables. So here we were looking at functions from R to R2 or R to R3. Next chapter, we would have functions from R2 to R, or R3 to R, or things like that. That would be our third chapter, and that's probably the kind of main subject of the book. That's the most important one in some sense. And then we would get to, after that, we would get to the hardest part of the book, actually, which is mostly about the integrals. It's called multiple integrals. We would talk after this. There's another fifth chapter, which I would only mention that a little bit. We wouldn't really dive into that. That's mostly about vector analysis. That's a quite advanced subject, like Stokes theorem and stuff. I would talk about that a little bit too. That would be our course. I would give you a sample exam. Yes, I would email you sample exam. Okay, that's it for today.